Rust ownership feels confusing until you see it fail and get fixed in real examples. In this video, we will go through 25 practical ownership and borrowing patterns that every Rust developer needs to understand. By the end, compiler errors like moved value and borrowed value will make much more sense. We start with the core ownership rules that make Rust different. These first examples show when values move when they copy, and how functions can receive or return ownership. Imagine we are processing a username once, for example, in a logging or import step, and we do not need it afterward. Let's write a function that takes a string, which means it receives ownership. Now we run it and see that the function prints the name successfully. Let's break down why this works. The string is heap-owned data, and Rust moves that ownership into process name. If we uncomment the last println, main would try to use a value it no longer owns. Now we show the best practice. Pass ownership only when the function should be responsible for the value from that point on. This keeps ownership flow clear and prevents accidental attempts to reuse moved data. For numeric IDs, counters, and flags, we often pass values through helper functions and still need them later. Here we copy an i32 into another variable, pass it to a function, and then print both values. Now we run it and confirm that Rust allows every use. Let's explain the result. An i32 is small, fixed-size data, and it implements the copy trait. That means assignment and function calls duplicate the value instead of transferring ownership away. Now we show the best practice. Use copy naturally for small scalar data like integers, booleans, and characters. But do not assume the same rule applies to heap-back types like string or Sometimes we need to send a message into another operation, but keep the original for later logging or UI display. Here we clone the string, move the clone into the function, and keep the original in main. Now we run it and compare both printed lines. Let's break down why the original is still available. Clone creates a new string with its own data. The function consumes only duplicate, so message stays valid in main. Now we show the best practice. Clone only when two independent owned values are really needed. If a function only reads the data, borrowing is usually cheaper and clearer. A common pattern is building a formatted value in a helper and letting the caller decide what to do with it. Here, build report creates a string with format and returns it to main. Now we run it and check the report printed by the caller. Let's explain the ownership flow. The string is created inside build report, but it is not dropped there because it is returned. Main receives that owned value and stores it in report. Now we show the best practice. Return owned data when the caller should store it, pass it around, or decide how long it lives. This keeps lifetime management simple at beginner level. Now we move from ownership transfers to borrowing. Shared borrowing lets a function read data without taking it away from the caller. For validation or measurement, a helper usually does not need to own the whole string. Here, namelength takes a shared string slice, reads the length, and leaves ownership with main. Now we run it and verify that we can print both the length and the original name. Let's break down why the final println works. The ampersand creates a shared borrow, so name length can read the data but does not own it. When the function returns, the borrow ends and main still owns customer name. Now we show the best practice. Use shared references for read-only helper functions. Prefer stir* for string inputs because it accepts both string values and string literals. In this section, we use shared borrowing for read-only access. The goal is to accept data without taking ownership, so the caller can keep using it after the function returns. In real code, greeting, logging, and validation functions often only need to read text. So we accept str, call the function with a string literal, then call it again with a borrowed string. Now we run the code and check that both inputs work. Let's break down why this works. The function borrows a view of the text, so it does not take ownership. The owned string remains usable in main, which is why the final print still works. Now we show the best practice. Use str for read-only text parameters. It makes the API more flexible because callers can pass literals, string values, and other string slices without extra allocation. A command parser often needs the first token from a line of input. Here, we return a slice into the original string instead of building a new owned string. Now we run it and look at the first word. Let's break down why this is useful. The returned value does not own text. It points at the first part of command. That means the slice is fast, but it can only live while the original string is still valid. Now we show the best practice. Return a slice when the answer is part of the original input. Use an own string only when the result must outlive the source or needs independent modification. Now we apply the same idea to collections. A function can inspect a vector through a slice, which keeps ownership with the caller. Imagine a task queue where we want to count pending work before processing it later. The count function only needs read access, so we accept a slice of string values. Now we run it and confirm that main can still use the queue. Let's break down the result. The helper sees the same 3 items, but it only borrows them temporarily. After that borrow ends, main still owns the vector and can read its length again. Now we show the best practice. Use for read-only collection input. It accepts vectors and other contiguous slices, so the function is more general than one that requires VACT. In this section, we switch from reading data to updating data. Mutable references let a helper change caller-owned values without taking ownership. An audit log is a good example of caller-owned data that grows over time. We pass a mutable reference into append event, push one new message, and then print the final log. Now we run it and look for the appended event. Let's break down why the new entry appears. The function receives temporary mutable access to the same vector owned by main. After the function returns, the borrow ends and main can iterate over the updated vector. Now we show the best practice. Keep mutation explicit and focused. Use one clear mute parameter when a helper is responsible for updating caller-owned data. A common backend workflow is changing an order after payment confirmation. We create an order, print it before the update, pass a mutable reference to mark paid, and print it again. Now we run it and watch the status change. Let's break down the output. Before the function call, the status is pending. After mark paid runs, only the status field changes to paid, while the order ID is preserved. Now we show the best practice. Put focus mutations into small functions with explicit mut parameters. This makes it clear which function is allowed to change the data and keeps ownership simple. In this section, we focus on rules that feel strict at first but protect real programs from unsafe shared mutation. The goal is to shape code so reads and writes happen in clear, non-overlapping phases. In real apps, a shared settings object is often updated from different configuration paths. Rust allows that, but only one mutable path can be active at a time. I am leaving the double borrow commented out so we can see what would fail. Then I use 2 scopes to update the same settings safely. Now we run it and check that both updates happen. Let's break down why this works. Inside the first block, settings is mutably borrowed only long enough to update the theme. When that block ends, the borrow is gone. So the second block can borrow settings again for retries. Now we show the practical rule to use in everyday code. Keep mutable borrows short, especially around shared state like settings, caches, or request data. Scopes make the lifetime visible and prevent accidental overlap. Imagine a shopping cart where we need to inspect the total before adding a discount line. We first read the cart through a shared borrow, store the computed total as a plain number, and then the read borrow is finished. After that, we can safely mutate the vector. Now let's run it and look at the updated cart. Let's unpack the borrow timing. The function receives an immutable slice, calculates a number, and returns it. Once we have that number, we are no longer holding a reference to the cart, so pushing into the vector is allowed. Now the best practice is to separate analysis from mutation. First, collect the facts you need, like totals, indexes, or flags. Then perform the write in a second phase where no old references are still being used. Now we move into structs, where ownership becomes more precise. Rust lets us move, borrow, and replace individual fields, as long as the remaining value stays valid. For a queued message, the body may need to move into a send function, while the metadata is still useful for logging. Here, the body is owned by the struct and sending it transfers ownership. We do not try to use the whole message afterward, we only use the fields that remain. Now we run it and confirm the body was sent and the metadata is still available. Let's explain the important part. Moving message body consumes only that string field. Rust then treats the struct as partially moved, so using message as a whole would be invalid, but using subject and priority directly is still fine. Now the best approach is to design for the ownership transfer you actually need. If a field is meant to leave the struct, keep it as an owned value and move it intentionally. Avoid cloning big content just to silence the borrow checker. In account code, we often need to display who owns the account while updating the balance. Instead of borrowing the entire account, we borrow only the fields we need. The owner reference is read-only and the balance reference is mutable. Now we run it and see both values printed together. Let's look at why the borrow checker accepts this. The references point to different fields, not to the same whole account value. Rust can prove that changing the balance will not change the owner string. Now the best practice is to borrow the smallest part of a struct that your code needs. This keeps other fields available and makes ownership intent clearer. Use full struct mutable borrows only when the operation really needs the whole object. A reset token should be consumed once and then disappear from the session. We store it as option string call take, and Rust moves the string into the token variable while putting none back into the struct. Now we run it and verify that the extracted value is sum and the session no longer has the token. Let's explain what changed in memory. The string is moved out, so there is no clone and no duplicate token. The option field is still valid because take replaces the old value with none automatically. Now the best practice is to model removable ownership directly. If a field may be present or already consumed, make it an option and call take when transferring ownership. This is usually better than cloning a token, body, handle, or other owned resource. Now we move into iterator ownership. These examples show when a loop borrows data, mutates it in place, or consumes it completely. In real apps, you often print or inspect a list before doing something else with it. Here we create product names, loop with a reference to the vector, and then run the program to confirm the vector is still usable. Let's break down why this works. The expression ampersand products gives the loop shared references, so each product is only borrowed for one pass of the loop. Ownership stays with the vector, so checking its length afterward is valid. Now we show the best rule for this pattern. Use a reference when the loop is only reading. It keeps ownership clear, avoids clones, and lets the next operation reuse the same collection. A common backend task is cleaning user input before storing it. Here we keep the vector, borrow each tag mutably, replace it with a lowercase version, and now we run it to see the normalized result. Let's unpack the important part. Iter_mute does not hand out ownership of the strings. It gives one mutable reference at a time, so Rust can guarantee there is no second writer touching the same item. Now we show the best way to think about it. Use mutable iteration for in-place transformations. It is direct, avoids building a second vector, and makes the ownership intent obvious. Imagine raw request text arriving from a queue. We no longer need the raw vector after converting it, so we consume it with into iter, map each string into an own command, and run the code to check the result. Let's break down the ownership here into iter. Takes ownership of the vector and moves each string into the mapping step. That is perfect, when the original collection is only a source for a new owned result. Now we show the best rule. Choose into iter when the old collection should disappear into the transformation. It communicates that each item is being moved, not borrowed. Next, we use lifetimes in practical code. The goal is not to memorize syntax, but to see how Rust connects returned references to the data they came from. In UI or logging code, you may want to choose between two labels without creating another string. Here we write a longest function with one lifetime parameter, call it with borrowed string slices, and run the program to see which label is selected. Let's break down the lifetime annotation. The function says the return string slice comes from either A or B, and it cannot outlive the borrowed inputs. Rust does not need to know which branch runs, only that the returned reference is tied to valid input data. Now we show the practical rule. Add explicit lifetimes when a returned reference could come from more than one input. Keep them small and local so the code explains the borrowing relationship without extra noise. Sometimes you do not want a struct to own data. You only want a temporary view into existing data. Here, document view borrows a document title from a string. Then we run the code and print through the struct. Let's break down what is on screen. The lifetime on document view means every value of this struct is tied to some borrowed title. The original string owns the text, and the struct only points at it while that owner is still alive. Now we show the best way to use this pattern. Keep reference holding structs short-lived and clearly tied to their source data. If the struct needs to travel far or live independently, store own strings instead. Now we move into APIs that feel flexible without hiding ownership rules. The next example uses cow, which lets a function borrow data most of the time and allocate only when it really needs to change something. In real apps, sanitizing text can be wasteful if most inputs are already clean. Here we write a function that returns the original string slice when nothing changes, and creates a new string only when invalid characters must be replaced. Now we run it with one clean username and one dirty username, and we print whether each result was borrowed or owned. Let's break down why this result is useful. The first input is already valid, so cow keeps a borrowed reference and avoids allocation. The second input changes, so Rust returns an owned string safely. The best practice here is to use cow when unchanged data is the common path. It keeps your API ergonomic while avoiding unnecessary string allocations. If every input must be changed, just return string instead. Next, we look at shared ownership in single-threaded Rust. RC lets several values point to the same allocation, while Rust tracks how many owners are still alive. Configuration is often shared by several parts of an app, and passing plain references can become awkward when owners live in different structs. In this example, we wrap one config in RC, clone the RC into two components, then watch the reference count rise and fall as scopes start and end. Now we run it and check the counts. Let's explain the count. At the start, only the config variable owns the allocation. Inside the block API and worker each own another RC handle, so the count becomes 3. When the block ends, those two handles are dropped and the count returns to 1. The best practice is to use RC only for single-threaded shared ownership. If a plain borrowed reference keeps the design simple, prefer that first. Reach for RC when values really need to be stored by multiple owners. Now we combine shared ownership with controlled mutation. RefCell lets single-threaded code check borrowing rules at runtime when static borrowing would be too rigid. Metrics collectors are a common case where several objects need to report events into one shared place. RC gives the recorders shared ownership, and RefCell lets them mutate the vec through borrow mute. Now we run the program and verify that both recorders wrote into the same collection. Let's unpack the important part. Each recorder only has an immutable self-reference, but RefCell allows mutation inside that shared structure. Rust still protects us. If we try to take incompatible borrows at the same time, RefCell will panic at runtime. The best practice is to keep RefCell usage small and local. Borrow, mutate, and release quickly so runtime borrow errors stay easy to reason about. If ordinary mutable references work, use those instead. Single-threaded shared ownership is not enough when work moves across threads. For concurrent mutation, Rust usually combines arc for shared ownership with mutex for safe access. A job counter is a simple example of shared mutable state across worker threads. Arc lets each thread own a handle to the same counter, and mutex makes sure only one thread increments it at a time. Now we spawn 5 workers, join them, and print the final count. Let's break down why the final value is reliable. Arc safely shares ownership between threads, and mutex serializes mutation of the integer. Joining the handles makes main wait until every worker has finished incrementing. The best practice is to keep the mutex lock scope as short as possible. Do only the shared mutation while the lock is held, then let the guard drop. After that, join all threads before reading the final value. The final example brings the patterns together at the API design level. Good Rust APIs make ownership visible in the function signatures. A task queue is a clean way to see ownership in API signatures. Adding a task takes a string because the queue should own it. Listing tasks only borrows self, and completing a task needs mutable access to update state in place. Now we run it once before completion and once after completion. Let's read the API through ownership. Add tax takes ownership of the title because the queue stores it. List tace uses an immutable borrow, so callers can inspect tasks without giving anything up. Complete tac takes a mutable borrow because it changes the queue. The best practice is to design signatures so the caller can see the ownership contract immediately. Use owned values when the API stores data, references when it only reads, and mutable references when it changes existing state. That is the practical side of Rust ownership. Moves, borrows, mutable references, and the borrow checker working together. If this helped, like the video, subscribe to Dev Level Up, and write in the comments which Rust topic you want to practice next.